Bon dia, molt benvinguts a una nova sessió del Cercle de l'Aigua. Avui, com vostès han vist amb el programa, doncs és una sessió amb el que intentem és demostrar el nostre compromís, el compromís d'Akbar amb la innovació. Ho hem fet moltes vegades i hem aprofitat la presència de Sandler aquí amb nosaltres per refermar una mica més aquest compromís amb la innovació oberta, amb el coneixement obert i d'aquesta mirada oberta a tot el món. Per tant, thank you, Leon, to stay here. And it's my pleasure to be here today and introduce to you Leon Sandler. He was born in Durban, South Africa in 1950, and since 2006, Leo Sandler has been Executive Director of the Deshpande Center for Technological Innovation of the Massachusetts Institute of Technology. The MIT is one of the world's most prestigious private universities specialized in applied technology. It has had, or we can see, or still has, a total of 78 Nobel Prize winners on its faculty. The winner of the 2014 Nobel Prize for Economics, Frenchman, Jean Tirole, completed this PhD at the MIT and is still a visiting professor at this university. It is a model of public-private partnership with a very open culture which encourage interdisciplinary projects. We would like the Spanish universities like MIT. The Deshpande Center was created in 2002 in the MIT School of Engineering thanks to a contribution from the Indian entrepreneur and multimillionaire Gurugah Deshpande and his wife Jaidi Antorn, the sister of the Indian IT giant Infosys founder's wife. Leon Sandler is an expert in recognizing disruptive innovation, those which have the virtue of taking giant leaps for humanity and for companies. Consumer habits are changing because of the introduction of these disruptive innovations. We have seen this very clearly in the world of mobile phones, where smartphones and companies like Apple have transformed the business and consumer use, leaving behind giants such as Nokia, BlackBerry, and Motorola. The business world is undergoing a process of transformation, and you know what your activity or what your business too. Akbar is committed to research, development, and innovation. I say that every day. And research, development, and innovation as a lever of business development and to maintain our position of leadership is the only way we can maintain the leadership in Spain and the world. A total of 225 dedicated professionals work in the group to develop innovation. This is our force, our resources, our innovators. But I said many times, all of people who works in Akbar groups have to innovate, have to be an innovator. All of us, we have innovators. Leon Sandler considers that many of the challenges that we now face will be met thanks to the hard and selfless work of the researchers. But, in his opinion, for this to happen, ideas must not stay in the laboratory, but rather be tested in the market. This is our force too. We can test it in the market. We have the market to test our innovations in the laboratory. To achieve this, Leon managed a grant program worth $1 million a year, which finances the projects of MIT researchers which the centers believe have the most possibilities of commercial success, like Spanish universities, you know. His role is also that of being in charge of seeking finance for the projects, which means maintaining excellent relations with venture capital funds, companies, private companies, government agencies, and educational institutions. The Deshpande Center is responsible for seeking funds for the research projects of the MIT and of its ecosystems, which have the most possibilities of success in the competitive real world. The latest projects which have received its support include research on cancer, arthritis, water desalination and purification, digital printing, nanoelectronics, the manufacture, and others. Over the last 10 years, the center has worked with more than 110 projects, from which 28 spin-offs have emerged with an investment of more than $400 million. The projects have to meet two requirements. First, to possess sufficient potential to have a social and commercial impact on the world, social and commercial impact. And second, to be viable from a technical and economic viewpoint. Leon Sandler's main task is to ensure that these two variables go hand in hand. This is very important. Hand in hand in these two variables is the key of the success. He graduated in chemical engineering from the University of KwaZulu-Natal in Durban, one of the most dynamic cities of South Africa, which has the most important port in Africa, as well as being the place where Gandhi founded the newspaper, The Indian Opinion, on his path in defense of the most disadvantaged and non-violent resistance. He likewise received an MBA from Stanford Business School. He has held important management positions in companies such as Boston Consulting Group, Eastman Kodak, Texas Instrument, and Digital Equipment Corporation, a pioneering company in the development of mini-computers taken over by Compaq, which was in turn subsequently taken over by Hewlett-Packard. Before joining the Deshpande Center of the MIT, he was the owner of his own consulting firm, the Mammoth Group, with which he helped the development of over 20 emerging companies in different technological sectors. He was also CEO of numerous startups and participated in many business projects as an interim executive or advisor. In the MIT, he was a mentor for 3 years in the service, helping students and faculties to seek funds for their projects. This service is the genesis of the Deshpande Center. One of the parts of his work which gives the most pleasure is his contact with researchers, helping them to market the new technology that they are developing. But this is not, however, only with researchers, but also with the collaborators and volunteers who form part of the knowledge ecosystems linked to the MIT, and with other entrepreneurship-related ecosystems. Entrepreneurship forms part of the culture of the United States, which attracts entrepreneurs from all over the world. Half of the executive directors of Silicon Valley companies were born outside the United States. Leon Sandler considers himself to be an eclectic person, which allows him to enjoy the so-called life science so much, as well as energy and materials and any other of the disciplines with which he works daily. As well as in his native South Africa, he has lived in Northern California, in Dallas, and for the last 22 years in the Boston area. He therefore knows I dare say, how to enjoy both the winters of New England and the beauty and magnificent climate in South Africa. We have a magnificent climate in Barcelona too. Huh? His interests include golf and spending time with his family. He has a teenager daughter and with his dog. As he himself admits, life and experience have taught him to stop suffering. Very important, to stop suffering. Suffering because of the aspirations that we all have when we begin our professional life, and to concentrate on enjoying life. And concentrate to enjoying life, because the environment is not very well today in Barcelona. You are concentrating enjoying life, and we can do in it, preparing himself for whatever may then come in his long journey as an entrepreneur, business facilitator, golfer, or father. Thank you for your attention. Thank you, Leon, to stay here, and it's your turn.
Okay. All right. Thank you very much. I would like to thank Angel Simon and Manuel Semeron for inviting me here today, for being such gracious hosts. I'd like to thank all the people of Aqualogy. There are a large number of them. I won't mention them by name, who have really put a lot of work into my visit here and have taken care of all the needs and really have made this a most enjoyable experience. And it's great to be with you today. So what I'm going to talk about is the culture of innovation and entrepreneurship. And I'd like to start with a little video. So I'm going to start with a little video, which should go here.
Where do my ideas come from?
I wish it was genius.
Ideas come from many different sources.
One place that they come from is actually just talking with people. You learn about what's actually needed, and you see these connections that you might not otherwise spot.
It's kind of a random walk process. You have an idea that excites you, you're trying to solve one problem, and you stumble across something else.
About halfway through my PhD, we had developed a new way of making complex microparticles. At that point, it was an interesting idea, but it didn't have any real application for it.
We had some simple pharmacokinetic models.
We were nothing more than some calculations on the back of an envelope.
I always had an interest in health. So we had started to think of how can we apply these particles to diagnostics.
We got the idea that we could scan ears for fitting hearing aids.
Come up with a battery that can store massive amounts of electrical energy.
A lot of things that happen in research labs don't necessarily turn into companies.
There's always questions around the technical merits initially, but really the key questions come from understanding the market. Where do you take it?
I thought if you have a great idea, of course you're going to have a great company, but it turns out that's not always the case.
Making things happen has got a lot of dimensions to it, and that's why this is so hard.
I'm at a point where I want to see technology get from the lab bench and be of service to society.
It's been such a rewarding experience. I love being a part of a small company. I love going to work every day. I couldn't imagine a different life.
Okay. So I thought that's an introduction, obviously, from some of the researchers, some of the people at the center. So let me talk a little bit about innovation. So what is innovation? What is it? Well, a number of definitions. It's finding solutions to human problems, doing something that hasn't been done before, that solves a problem for people. And that means really producing a product or a service that people find valuable and will buy. So I think it's important to note, in innovation, it has to be something that people find valuable enough that they will buy and spend money for. Otherwise, it's just an interesting project. So why is innovation important? And Mr. Simon spoke a bit about this, but it's important for a few reasons. And the one is, at a global level, innovation improves the quality of life for everybody. And also, innovation increases economic prosperity. So let me go to, I just want to give you a sort of historical example. For those of you in the room who are closer to my age, you may recognize this. The young people won't. This, when I was at university, this is what a computer looked like. That whole room is one computer, and we had one computer on the whole university campus there in South Africa. Now you go to today, that's what a computer looks like. That's a computer. It is millions and millions and millions of times more powerful than that whole room. It can communicate with every computer in the world, do all sorts of things, make phone calls, take pictures, things we couldn't have imagined when I was a student. So there's sort of an example of technological innovation. So who are the innovators? Who are these people who do this? Well, they're people who have a really strong desire to solve problems and who want to build. They want to build and create something. They are people who are intellectually curious. Innovators are very curious about how things work, what can be done. They like to explore things intellectually. And there are people who like to experiment and try new things. They are not scared of trying new things. In fact, they enjoy the experimentation. So what I'm going to do now is I want to tell you a few stories. So we'll spend maybe, 20 minutes. And I'm going to go through a few stories, really, from the center that I run to give you a richer picture of some of these things that go on. So if we look here, here is a patient. For those of you who have gone to the dentist and had to have a cap or a crown made, here's what happens. You would go to the dentist, you bite on this silicone, and they make an impression. Take this impression. They send this impression off to a special laboratory, a special place that then makes the part. They send it back to the dentist, send back the cap or the crown, and the dentist fits it to your teeth, and it may fit well and it may not fit, and the process takes about 2 weeks. So in 2002, when the center just started, one of the professors, actually one of the people on that video, came to us with an idea, and he's an expert in imaging. And he said, I believe that I can create something which will be more like a toothbrush that the dentist can use, but he moves it around somebody's mouth, and it will take an image of the mouth. So you can digitally image the mouth. It creates a file with precise dimensions. That could then be sent out to a machine that can then make the part. So digitally scan the mouth in a matter of minutes and then machine the part. And in fact, they managed to spin out a company to do exactly this, and today that's what happens. Somebody goes to the dentist that has this type of equipment. They scan the person's mouth. You sit, you read a magazine. This data is sent to a machine. It programs it. They machine the part right in the dentist's office. An hour later, he brings it back, and the tooth is done. And here is a short, very short video of this actual product. So it's scanning his mouth. Okay. So that's one of the examples. Then in 2006, we're approached. Fellow on the right-hand side is Professor Donald Sadoway in material science, metallurgical processes, and this is his student, David Bradwell, just finished a master's, was about to start a PhD. So the problem they were looking at is one of energy storage. And here's the problem. You understand solar energy in Spain because you've been paying large subsidies to have all the solar put in. You have wind power. Here's the problem. With solar and wind, the systems produce energy when the sun is shining and the wind is blowing, but then they don't afterwards. You can't just switch them off. So what you want to do is you want to take that energy when it's being produced, or the excess energy, you want to store it, and then later on, you want to be able to use it, maybe at night or when it's not windy. But in order to do that, you would need very large batteries. You need a lot of capacity, and you need batteries where the energy can come in and out very fast. So these two guys had an idea. They were experts, or the professor was an expert in metallurgy. Now, I don't know if any of you know what that is, but that is what the Americans would call an aluminum smelter. The British would say an aluminium smelter. And in fact, it's hard to see on this photograph, but that is, going back there, that is about as long as several football fields. Very long. And how do you make aluminum? What you're doing is you're taking, I'm assuming you guys are all technical in here. You're taking aluminum oxide, and you have to strip off the oxygen, and as you good chemists know, it's a low energy state. You have to provide a lot of charge, pump electrons in, and through a chemical process, you pull off the oxygen, and the metal that comes up is actually in a much higher energy state. So they build these smelting facilities right next to hydroelectric power plants. You need that much energy. And he said, wow, if we think of this as a model, is there a way we can build something with molten metals where we put all this charge in, but instead of it going to just straight aluminum and then this gas comes off and it can't go back, we could somehow reverse the process so it could go both ways. And so we could take something like this and turn it into a battery. So this was an interesting idea, we thought, and to give you a little more technical depth, because I work at a technical place, so we have to talk technology. So how does it work? So here's the concept. If you look on the side, what you have, and this is a molten metal battery, it's running maybe at 500 degrees Celsius. You have an alloy at the bottom, and that's magnesium and antimony. So these metals are alloyed, and they're in a molten form, and there's a molten salt on top. Now, what happens is, again, for the electrochemists in the room, you will know that when the metals alloy and they bond, that is a low energy state. When they bond, you're in a low energy state because of the chemical bond. But if you were to apply a charge to this, so now your solar cells are generating electricity, the electrons flow into the battery, they carry with them a charge. The charge adds energy. And what you're able to do now is break the bond between the magnesium and the antimony. And the magnesium, similar to the way we did this with an aluminum smelter, the magnesium now floats free, and it's actually lighter, so it floats up to the surface. So now you have this, think of it as a liquid battery, except it's very hot. Magnesium at the top, a layer of salt which separates them, and now you have this alloy at the bottom. And if you were to require to take energy from the battery, well, all that happens when you take the energy out, the electrons flow the other way, take the charge, the magnesium flows to the bottom. The advantage of a battery like this is when metals are molten, the electrons can move through extremely rapidly. In a solid metal, it moves very slowly. So we funded this project in 2006. It took quite a long time. It took about 5 years in the university. Ended up being quite a big project, required a lot of money from the outside. But then they spun out a company, raised quite a lot of money. And here is a picture. This is Dave Bradwell again, and this is one of their first modules that they actually produced this year. It's producing these. So that module he's standing next to, that will store about 40 kilowatt hours of electricity. So 40 kilowatt hours is, if depending on the size of the house or apartment you have, that will be about 1 to 2 days worth of electricity. But the way they designed this, you can take that module is sized, so if you took a standard shipping container, if you drive by the port of Barcelona, you just see thousands of shipping containers. A standard one is about 20 feet long, which is about 6 meters. But those are designed so they can stack 2 next to each other and 2 on top all the way through. So in 4s all the way into a shipping container. You fill up a 20-foot shipping container with those, and now you have about 1 megawatt of capacity. So, sorry, 1 megawatt hour. So what would 1 megawatt hour be if you take the Agbar Tower? I estimated based on the number of square meters and averages, that would probably be about 1 hour's energy use for a tower of this size. So maybe if you put 5 shipping containers in the basement, you could have 5. So let's go to the next scale. What about looking at the country of Spain? Spain has approximately 5 gigawatts of solar capacity. So it's 5 gigawatts, which is about 5,000 watts of solar capacity. So if you wanted to store energy for 1 hour's worth of energy from all the solar fields in Spain, that would be about 5,000 shipping containers. So you say, I need 5,000 shipping containers. So you may ask, well, how big? How much is 5,000 shipping containers? Again, just go down the road, go down to the port. 1 container ship will hold between 10,000 and 15,000 shipping containers. So if you think of the size of 1 container ship filled with these things, could supply enough energy, enough energy to take all the solar energy in Spain, and that would give you 2 to 3 hours of storage. So again, very, very interesting technology. Let's move to another field. So I'm going to move from here, seeing your people in the water business. Now I'm going to talk about a water project, but in a very different field from what you guys do, and at a very different scale. So here's the problem. One of our professors went to speaking to a doctor at a local hospital, and they said, we have a problem with drug delivery to the bladder. We want to deliver drugs to the human bladder. We need drugs that can stay in there for about 3 weeks for a number of treatments. There's a lot of conditions, but we don't know how to do it. And so he came to us and he had an idea. And he has his idea, and I'll just walk you through this very quickly. On the bottom, you can see there's a rubber ring. He said, I'll come up with a hollow tube made of silicon, make it into a rubber ring, and I'll drill little holes in it. And we'll fill that with the medication, the drug, in a powdered form, very concentrated. Then when the doctor, when they examine the bladder, they have a device, medical device they put in there. They can just squash this rubber O-ring, shoot it up into the bladder, and it can sit in the bladder, and later on they can take it out. So how does it actually work? If you look at the top, it works on the basis of an osmotic pump, and the guys who are at SET Aqua should understand this right away. The osmotic pump, the silicone tube is a membrane. It's a semi-permeable membrane. So water can permeate in, the solids cannot come out. Anything dissolved in the water. It permeates in, it dissolves the medication, dissolves the drug, and then it's actually pumping it out. So what comes out through the holes is the medicine dissolved in water, but by doing very sophisticated design of the plastics, design of the porosity, and designing this, you can have these things deliver drug over a period of 3 weeks in the bladder. So initially, the first year, they tested these just in the lab on benches, then in rabbits. Then they spun out a company. It's raised a lot of money. This product is being used in people. That's just a quick picture. I won't go into it. What the actual design looked like, you can see on the one side, and then a zoom in. That's the actual product, slightly different from the drawing, but this is a very successful company. Okay. Again, this one is a little more technical. We'll go into this. So here's what we have. A biologist came to us. Biologist said, I've made a very interesting discovery. So in the human immune system, those purple things you see are called neutrophils. We all have them. Neutrophils are part of the immune system that will go and attack foreign things in the body, bacteria, viruses, things that shouldn't be there. They attract. And what they'd found in their research that these neutrophils were attracted to a particular carbohydrate, which is a type of sugar, carbohydrate or sugar, that they found in a fungus. And if you think of like a bee going to pollen, they would go to these things. So they said, we think this could be quite interesting for solving a problem in cancer. And what's the problem with cancer? With a lot of cancers, the body doesn't recognize the cancer as foreign, so the immune system does not attack it, and the cancer just grows. So they said, if we can take these, can we use this? And what happens, they said, can we attach these carbohydrates to things called monoclonal antibodies? Monoclonal antibodies are very specific for cancers. They will go and attach to specific cancers. They're easy to find. If we attach these, then the monoclonal antibodies are going to go and attach themselves to the cancer cells, and they'll have these little carbohydrates dangling off them. And then what happens is the body's immune system, the neutrophils, are going to go in, be attracted to these carbohydrates and antibodies, and destroy the cancer cells. Again, project we funded, it took several years. They tested this. They did some tests with mice. It seemed to work very well with mice. And they've also spun out a company that's now doing further tests. It's a long way to see if it works in humans. A few other examples. I do see several people here wearing glasses. So I know, you all know what this is. But, how old is this technology? This is it's like water treatment. It's been going on for a long time. We've got a lot of other things. Remember that phone we talked about earlier? Well, what if you could do this? What if you could, take your phone out, put this optical piece on, you put an application on your phone, bit of software, you look through this thing, you see two lines that aren't in line, you go click, click, click on that little volume control on the side, the lines come aligned, then you push something else, you see two lines this way, click, 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 you're done. That's the prescription of that eye. So again, project we funded. This is in a company. It's actually being built and deployed, which allows you to measure prescription. Probably, in Spain, in America, it will take a bit of time. But if you're in India, developing countries, very, very interesting application. Solar. We talked about solar earlier. So, I know the Spanish taxpayer has been paying a lot of money to subsidize solar. Why? Why did you subsidize solar? Well, because it cost more than, coal-fired, oil-fired gas plants, because the polycrystal and silicon solar cells are expensive. Well, one of the reasons you say, why are they expensive? Because they make these things the way they make semiconductors. They make them in wafers and they chop them up. But do we make glass that way? Do we make steel that way? No, we don't make those things that way. We make those in a continuous flow process. The glass flows, the steel flows, and then you chop it up. And so we have one of our projects that had an idea for being able to make silicon solar cells in a continuous flow process. And their belief is by improving the manufacturing process and making it much, much cheaper, they can drive down the cost of solar cells very, very significantly. So again, they've spun out a company. This company has raised a very, very large amount of money. They've done prototypes. They've got manufacturing plants they built, and they plan to sell these cells. And that's enough of the stories. So now I've told you some stories. Hopefully that's given you a flavor. That's maybe 4 out of 28, so just a flavor of the stories. Now I want to talk a little bit about how do we do this stuff. What do we do in terms of innovation? So doing innovation at the Deshpande Center, the first thing you have to look at in any organization is what's your mission. So what is our mission? And Mr. Simon talked a little bit about this. Our mission at the center is to create impact in the world through technological innovation. That is what we want to do. We want to move MIT technologies from the lab out into the marketplace, and we want to stimulate innovation at MIT. It's actually not, we're not trying to make money. These things have to be self-sufficient, but it's to stimulate innovation. But there's more, and I know there are some educators in the audience, because we're an educational institution. And so we have a second mission, and that mission is educational. We want to educate faculty and students about the process of how you commercialize technology. We want them to go through our program and learn how to do this. But we don't run classes and we don't teach them in lectures. The way they are going to learn this is by actively being involved in these projects and doing it. And so, how do we do this? Well, let me step back from how do we do this. I'll talk about what's the problem we're trying to solve. As a good engineer, we always look and say, what's the problem? How do we solve? So here's the problem. So on this side over here, you have academic research. Academic research goes on at a university. We discover interesting things. We work on some interesting stuff. However, in order to have innovation, you need a product that people can buy. You need a product. Universities don't produce products. Products have to be produced by commercial entities. So you need a commercial enterprise that is going to produce that product. And here's the thing. You've got to take the stuff in the lab where there's things on the bench, but to turn it into a real product takes a lot of work, a lot of engineering, a lot of design, and that takes money. A lot of money. So for every dollar or euro you spend at the university, somebody is going to have to invest 10 to 100 times that in the company just to produce the first product. So somebody has to come up with that money. That could be a large company, it could be venture capital, it could be the government, it could be it could be anybody, or a combination. And there are two things that those investors, we'll call them investors, are going to look at before they make the investment decision. They want to know, what is the technology risk here? What's the risk? If we put our 10 million euros in, what's the risk that we actually get a product out or we don't? And what's the market risk? If we build this wonderful thing, if we build this device to scan teeth, is anybody going to buy it? And let me go into a little more depth on those. So technical risk, what you're trying to do is really understand, is this technically feasible? Can you somehow prove or show that the key technologies work, that this doesn't defy the laws of physics? And you need data. You need to show people data from experiments that this will work technically. But also, what is the performance range of that? What this means is, how well do you work technically within a certain range? How much energy can that battery store? How fast can it go out? How heavy is it? How much does it weigh? So you need to do stuff in the lab. You're not building the product. You have to show it. And then there's market risk. And the market risk is, will this product be competitive? So people will buy it. Well, we'll come out with a new battery, but how does that compare with lithium-ion batteries, lead-acid batteries? Is it going to be better? And what's important to the market and the customers? What is it that they care about? And what are the technical performance requirements that the market has? So the market has requirements technically. On the previous slide, there's a performance range you can be in. Do these overlap? So what we do at the center, if you remember that chart where we had the university, the company, and the problem, people are looking at technology risk and market risk. What we're trying to do in a time period of, say, 1 to 3 years is reduce the market risk, reduce the technology risk to the point where an investor says, this looks like a good decision. This looks like a good investment. So it's, what can you do over a period of 2 years to show investors that the technology risk is reasonable, the market risk is reasonable? And that's what we look at. So how do we do that? So I like to say our process, there's three things. We select, we direct, and we connect. So what does that mean? Select means that we pick projects. Selection is which projects do we pick? We want to pick projects that we believe have a chance of commercialization. They may be very risky. We do not mind risk, but it's projects that have a chance of being commercialized if they had another year or two of research in a specific area. Direction, what we want to do is we want to direct those projects. We want to move them in a direction that reduces the technical risk, that reduces the market risk. How do we do the directing? Well, we do some of that from the center, but what we have built is we have built a very large group of mentors. We have about 50 mentors, and we have an ecosystem of people around us we can bring in so that we can help, all of those people can help steer and advise and guide our projects. And we connect. Connecting is very important. We connect people to the marketplace. We connect them to companies. We connect them to customers. We connect them to investors. We connect them to fellow team members who may be able to work with them in the research stage or work with them when they spin out the company. So I'm going to go through this quickly, but Mr. Simon mentioned some of these things. Oh, sorry, that's the next slide. Let me go through what we do. So let me go through this on a different basis. What are we really looking at? So where we start, this is a graphical representation. Somebody comes to us with an idea. They come to us with an idea, and it goes through our selection process, and what we will do is we'll give it a small amount of funding. We call that an ignition grant. So it's $50,000. We give them $50,000. It's 1 year, and they work on this project, and we want to see where they can go. At the end of the year, if the results are not good, it's over. If the results are good at the end of the year, we will give them more money. It could be up to another $200,000, maybe less. And that we call an ignition grant. And at that point, we're really finished at the center. And what we're looking for is during that period, again, can we reduce the technical and market risks? Can we prove the concept so that the technology is then ready to spin out of the university? And typically, most of these will spin out into a small spin-out company, which is going to worry about the commercial world producing and selling the product. And ultimately, if this is successful, either that company will grow into a large company, or in a lot of cases, it will be purchased by a large company, it will become part of a large company, and then will grow. Okay, next slide. The history. So let me talk a little bit about the history and the results. So we have been around for about 12 years. We've now reviewed over 500 proposals that we've had a review. We've funded 120 projects with about $15 million. So if you do the arithmetic very quickly, you say that's about, the average is about $120,000 per project is the average amount, some lower, some higher. And what are the results? The results are that we have now worked with over 300 faculty and students and over 100 volunteers. From that, we've seen 28 startup companies formed, and those startups have raised over $500 million of capital, and they employ hundreds of people. And if you can look at that, what that really says is about 20 to 30% of the projects we fund spin out into companies, and the rest of them don't, which we think that's about appropriate level because we like to do things that are a bit risky. Okay. What have we learned from this? So we've been doing this for 12 years. What have we learned? Well, here's what we've learned. It's very important to understand the customers and the markets as well as the technology. Even though we are in the business of technological innovation, it is critical you understand the customers and the markets as well. People are absolutely key. Technological innovation is not done by machines, it's done by people. And the type of people you need are people who are both broad and deep. Somebody once said T-shaped people, like the letter T. But what does broad and deep mean? So what broad means is you want people who can think in various areas. They're interested in other domains, other technologies, things outside of technology. They need breadth. They need to see things that are outside of the specific area that they work in. You need the breadth, because that's where the ideas come from. But you also need people who are deep. If you want to do something technically, if you're going to do something in chemistry, you better be really deep in chemistry. If it's going to be in mechanical engineering, you need to know mechanical engineering very well. So you need this combination of people who are deep and who are broad. And it takes creativity. You have to be creative. These people are creative. They have expertise. And it also takes discipline. This is hard work. It takes a lot of discipline to do this correctly. The other thing is risk. So you need to be willing to take risk. But you need to manage the risk. So there is a difference between taking a risk and being bold or being reckless. And how do you manage risk? And the way we manage risk is by placing very small bets initially. You put a small amount of money into something very risky, and if it works, you give it more money. But you want to take risk, but you need to just manage that risk very carefully. All right. I'm going to change directions now because I said I talk about innovation and entrepreneurship. They are very different things, but they work together very well. So let's talk very quickly about entrepreneurship. What is entrepreneurship? So I went onto the web and I did a Google search, and here's what I came up with. Entrepreneurship: develop, organize, and manage a business venture. Sounds okay? Entrepreneurship: starting and building a business. Entrepreneurship: creating something where there was nothing. And then the last one, which I actually like the most, entrepreneurship is about pursuit of an opportunity beyond the resources controlled. So it is about having constraints on what can be done. You have limited resources and you have to get something done. You don't have all the resources you want. And to me, that's the others are good definitions, but this is a very interesting definition of entrepreneurship. So, can entrepreneurship be taught or learned? And the answer is yes, it can. People say, oh, you have to be born an entrepreneur. We've seen time and time again. Absolutely not true. People can learn the skills and they can learn the attitudes. Entrepreneurship, it's a team activity. The idea that it's Steve Jobs, it's Bill Gates, it's this, that's a very interesting fiction. The bottom line is entrepreneurship is about teams. Even if you look into any of these things, there's always a team of people. There may be one personality that's bigger than the others, but it's always a team that gets things done. And entrepreneurs have to be able to work in teams, lead in teams, be part of teams. Entrepreneurs need to think differently. So, how do they need to think differently? Well, they need to think like a pirate, not like the Navy. Why is that? Because resources are limited. So you have to think like a small military unit, not the whole army. You don't have the whole army. You have limited resources. Entrepreneurs have limited resources, so they have a very clear understanding of the mission and what needs to be done. They have to be very focused. You cannot do everything. You have limited resources if you're an entrepreneur. And they have to do very creative problem solving. Again, The resources are limited. You can't come up with expensive solutions. You have to figure out, how do I get this done with limited resources? And they have to make decisions rapidly. Time uses resources. You burn resources. You're paying salaries. So you need to make fast decisions. It's okay even if they are wrong decisions. You make the decision, and then you make another decision. So what's the challenges for a large organization with entrepreneurship? Well, you've got the problem of conformity versus entrepreneurship, which is being an entrepreneur in a large company. Large companies, people find it safer to conform rather than being an entrepreneur. Risk avoidance. Well, large companies, risk can be a dangerous thing. But to be an entrepreneur, you have to take risk. What's the culture? Does the culture let you take risk or doesn't like you to take risk? You want to be safe? Slow decision making. Now, I know that never happens in any large companies, that just but you want a decision, it's got to go up to the committee and to 6 levels of management and up and down. So you need to have a way of looking at it. In a large company, delegate decisions down so that certain decisions can be made very fast. And then finally, rewards and punishment. So I like to ask this question to we get a lot of visitors at MIT. These guys from large companies come, they see us, we talk to them, it can be any company, and they say, we're very entrepreneurial, we like to do this, and I say, I want to ask one question. Somebody tries something at your company and it doesn't work. Do you promote them? And people look at you. So one of the things you have to think about, though, is what is the system in the large company? Does it reward this type of behavior, or does it punish it if something goes wrong? Quickly, because I know I've got 1 minute to finish here, let me go through the entrepreneurial steps. Very simply, what do you do in entrepreneurial steps? You need to define a product. You then need to understand the customer and the market. But then you find out that that's not quite what your product was. So you have to go back and redefine the product, and there's a circle. Then you look at the business model. What is it that you are going to be doing in your business? Which part of this are you going to do? And once you've decided on that, you then look and you say, well, gee, is this the right customer, the right market, and the right product? And you have to go back again and look at it. And then you have to look at what's the economic model? What's the economics of this? How do we make money? What's it cost? Are we buying it at 10 euros and selling it at 15 or selling it at 5? And so you may have to go back and look at the business model and the customer and the market, the product. It's a very iterative process. It's not putting a plan in place and executing. So entrepreneurship is very iterative. So I want to leave you with final thoughts for the audience. Here's my challenge to you today. So I want to ask all of you, even those people in the back row up there, be an innovator and be an entrepreneur. And my message is the following. You can do it. Each one of you can do this. All you have to do is the following. Ask yourself, what are your natural talents? Everybody has natural talents. They're different. What are your natural talents? And what are you passionate about? It has to be something you feel passionate about. What is it that you're passionate about? And what gives you joy? What makes you incredibly happy when you're doing it, when you see it? What are those things? And then once you figure that out, go out and change the world and go and make it a better place. And I will stop here. Thank you. Thank you.
Thank you, Leon. Very good speech. I enjoy it. Some specific ideas. Move from the lab to the marketplace as soon, as fast as possible. To learn by doing. I think this makes the difference between us, Spanish people, and Anglo-Saxon people. This is the difference. People are key, but in a team activity. And you made a very good description for a large French company. Very good. And it's true, be an innovator and entrepreneur. Thank you. And let's start the questions and answer sessions. And Manuel Cermeron, I think if you can summarize the questions, it will be for the session. Thank you.
Thank you. First of all, Leon, thank you very much for this very informative and interesting presentation. As you can see, I have here a nice bunch of cards with not hundreds, but quite a decent number of questions. It's going to be impossible to go through all of them. So I've tried to package all of these questions in blocks and just to try to touch the different subjects that has been raised by the audience. The first question has to deal with market orientation and open innovation, if you want, is what is the role that you let the big companies to play in your center? Once you have decided you want to grow up an idea, what is the role that they are going to play?
Okay, great. I think we have very good relationships with a lot of large companies. I think the role there are a number of roles. One of them is large companies understand the markets they're in. So they're the relationships with them are very valuable in order to talk to those people and say, here's what we're working on. Please give us input. What does this product have to look like? What does it have to be for the market? Where does it have to go? The other role is some of our projects will need additional research funding. They may be products that should naturally go into a large company, so we see that as well. But it's a two-way street. The large companies come to us, they're looking for technology, they're looking to see where they should go, and we are looking to them to get their advice, input, and expertise.
A second one is you have been talking about some examples of projects going to the market. And the question is quite very short, is in average, how long does it take from the idea to arrive to the market?
That's a good question. So we get asked that a lot. So I think I'll break it into two parts. If you can remember that chart I had with the arrow, and there were two parts. There's the part where it stays in the university and then the part after the university. So if you look within the university, from the time we get it at our center till it leaves the university is probably 2 to 4 years. Now, you might have research that has been going on for 10 years on a domain before it's ready to come to us. So sometimes there's basic research. But from the time we start working with it, when we think it has commercial potential, we've had some that have been as short as 1 year. Others have taken 5 years, but I'd say 2 to 4 years. Now, the next question is, okay, now it's spun out of the university. How long does it take before you have the first product that somebody can buy, or the first service? Probably the shortest I've ever seen is maybe 18 months, so a year and a half. But I would say typically it's at least 2 years, could be up to 4 years. And if you're talking about a product that is going to be used in the medical field, go into human use, because of all the regulations and the tests, that could take another 6 or 8 years after it leaves, just because the testing is so long. So, if you said from start to finish, probably the range would be maybe 4 to 10 years. So I think you have to have the right time horizon here. This doesn't happen overnight.
Thank you, Leon. You during your presentation, you talk about listen to the market. So that here we have a very interesting question is, what is your opinion about the sentence, customers don't know what they want?
Okay. So I was telling people the other day, let me tell you what my thought about that is. I hear that a lot from people who are having trouble selling something because they're not producing what the customer wants and needs. The customer is always right. They're the person with the money and they're going to buy. So the question of the customer may not be able to explain to you what they want. They may not see it, but I assure you, the customer absolutely knows what they want. And it's often a question of how you go out and how you ask them and what you want to do. You don't typically go out and say, sometimes you can say, hey, if I can produce this product to scan teeth, would you buy it? But you may need to really understand what are they doing, why will this bring them benefits. But ultimately, if you have a good product and you bring it out and it's basically satisfying a need for the customers, it's fairly obvious to the customers what they want. And I think in researching it, you can absolutely find out what they want. So I think the customers, if you ask the right questions, they know what they want.
Now, if we talk about open innovation, how important is open innovation for your center, and how you guarantee that you have the proper external insight as well as the internal insights in the IT?
So, we may look at open innovation a little differently because we're a university. So typically, when a company looks at open innovation, they're saying what we want is to bring new innovations into our company. I think for us, universities are very open places. MIT is very open, by the way. You can walk right in off the street. There's no security. We like to say we want a very porous boundary between the university and the world. We want ideas to flow. So for us, we want idea flow into the university, out of the university. Universities publish things. If we're working on something, any of the projects in our center, we may file patents, but we always publish. We want to share that with the world, so we may want to file patents. And the reason we file patents, by the way, is because that makes it easier to get a company started. But I think open innovation in the sense of discussions with people who are working on things, being aware of who else is doing is important. We don't, at the center, we're not looking if there's a project, let's say in energy, we don't dig into that, but we expect the team will stay in contact with anybody who's doing it, have discussions. So I think open sharing of ideas is how you get the best ideas. 1 and 1 equals 3.
Yeah, another one that can be very interesting as well is all this openness includes the Russian talent? Russian talent?
Russian talent? So I think the issue, so I'm not quite sure what that question means, but so I think the thing is in an academic area, again, you want to be fairly open, sharing things. We're typically, maybe you're alluding to, obviously there are things that are done in the US. It's more, let's say, in our aeronautics area, in some of the electronics area, where there might be restrictions by the government on what can be shared with different countries. But I think, when we work on foreign collaborations, we work with other people, it's not going to work unless you can have an open discussion. So what you really want to do is pick an area. If there's an area that's going to be restricted for national security, government reasons, then that's not an area to be collaborating on. But we want it to be very open.
Okay, if we move to startups, big corporations relationship, do you think that is feasible to make big corporations work alongside the startups to enhance innovation results?
Oh, absolutely. And what I've seen, it's interesting, I'd say over the last 5 years, what I'm seeing is a lot of very sort of leading edge big companies, some of the big pharmaceutical companies, Roche, Sanofi, some other companies, Shell, 3M. These are these big companies that you would have thought in the past they were all doing stuff internally. It was all internally focused, internal R&D, are all very actively out there engaging with us, engaging with startups. They're investing in startups. They're working in startups. And there's a lot of different models where they will try and partner with startup companies. Sometimes they will acquire them if it's core to their business. Sometimes they won't. They will just have relationships with these companies. But essentially, I think large companies and startups, again, if it's done correctly, they can coexist. It has to be a relationship that is based on sort of trust and works well for both parties.
You mentioned a sentence, need to be broad and deep. Do you think that this is possible, or we are going to need a middle person to bridge the gap?
So I'll answer it in two ways. Not only do I think it's possible, I think it's essential. It is essential. You cannot have somebody who, if you want to do innovation, if they've just sort of sat in one area all their life. You want people who maybe people get inspiration. Yesterday, I was looking at the Sagrada Familia, and what was the story? The guide was telling me about how Gaudi got a lot of his inspiration from looking at palm trees and how they supported things. That's how he came up with the pillars. So people get ideas from outside. I think they need to be broad and deep, but the way, in terms of having a bridge, is you have multiple people. So if you look at your team, you're going to have somebody who's much better at understanding markets, somebody who's much better at engineering, but you don't want your engineers to just be in the laboratory. I like the idea of kick your engineers out occasionally. If you have a trade show, go have them work with the customers. You want your marketing people to come into the laboratories because you really need that sort of cross appreciation of what's going on.
Great. I'm trying to wrap it up with a session of questions. You have been talking about innovations and inspirations in your center linked to engineering, energy, and the medical field and things like that. What about water?
So we have a few projects right now in the water field. Again, the way we're set up is essentially we just request proposals from anybody in any field, be it electronics, you name it, water could apply to us. But we have one project in the desalination membranes area that started about a year ago. It's fairly radical. It's a new way of doing it. The results of the first year have looked good, but it's got a long way to go. And it may make it, and maybe this year when they get the technical results, they'll work, maybe it won't work. And we have another two projects that are in the water area that just started last month.
Thank you. About the role of the state, that plays the state in the administration in your center. Two questions here related with that. One is, what is the role of the state that plays in the center that you are leading? And the second one is, what is the role of the Desh family in the center?
Okay. So the role of the state, let's see. Well, they come to ask us for advice, but that's, I was going to say, we have people flying up from Washington, from different government departments who come to ask us for advice. But essentially, and we have a very good, we're happy to talk to them. But the state itself, and there's two levels of state. There's the federal government in Washington, and then there's the state of Massachusetts, which would be like Catalonia that we live in. So the state actually doesn't play any role at all directly in the Deshpande Center. They aren't providing funding. They aren't providing any resources to us. Now, That's not the same. We talk to a lot of people all over the world. I think in a lot of parts of the US, if you have universities that are funded by local state institutions, then there is state money because it's hard to get the money. So in most places, there's a level of state money going into these things. But again, we just maintain a good relationship with the government. The important part, though, at the university, at MIT, is the government is funding a lot of the basic research. Most of the basic research is funding. So government funding is critical. If you look at a lot of our projects, there's government funding. Let me give you an example, though. That battery project, so we put in $250,000, which is the maximum we could put in. There was about $4 million after us because it took a lot of work. $4 million came in from Total, the French oil company, and then there was a $7 million grant from the United States Department of Energy. So although that didn't come into the center, there was a lot of government money and corporate money that came in after us because there was just so much technical work. You asked about the role of the Deshpande family. Deshpande is a very interesting guy. He's a very wealthy, successful entrepreneur. He's a very humble person. If you meet him, you wouldn't know. But very philanthropic. He lives in a reasonable house, drives a normal car, but he has a charitable foundation. They have programs to feed people in India, a lot of things, and he's does not get involved in the direct management of the center. He sits on our board of directors, but he comes to all of our events. So he will come to our symposiums, he'll come to functions, and he's always available if we need him.
Attending to the different projects that you are dealing with in your center, what technologies will drive the biggest changes over the next 5 years?
So actually, that's a very easy question to answer because of one of my previous answers. And so the biggest changes over the next 5 years is actually none of the projects that we're currently working on because it takes so long to get out there. But, what are some of the interesting ones that I didn't mention? We've got a really interesting project for oral cancer treatment, for local delivery of drugs for oral cancer. If that works, we'll find out by January. They're doing the tests on the hamsters in the next few months. It looked great initially. I think that could be very interesting. This water desalination one, it uses graphene. If that works, it could be. One of the things I'll just reflect on, somebody asked me this earlier today from your communications thing, what do I like about the job? What's sort of and there's a lot of interesting things, but one of the things to me that is just sort of fascinating is when you can, because I've been doing this 8.5 years, when you can see somebody that Don Satterway and Dave Bradwell, I remember when they presented this idea in a conference room, and it was just an idea, but with some good science behind it. And to be able to watch something like that, it's like planting a little teeny seed in the ground, and you sort of watch it come up, and you watch it develop over time, and then at some point you have this big tree with fruit. And so to me, watching these things develop is very satisfying. It's hard to know which ones will look good. It's sort of like, you have all your children and you love them all, and you don't know where they're going to end up.
And now the final one.
Yeah.
The first part is not a question. You know that in this city we have the best soccer team in the world, okay? So that's
absolutely, okay. I have to agree with that.
But the question is, meet MIT or Stanford, who is producing the best engineers in the States?
Well, it's an easy question, it's a difficult question. Here's the problem. I'm a Stanford graduate, but I work at MIT. And the other problem is, I am in the School of Engineering, So the Dean of Engineering, I have to be very careful. But I would say, actually, I think they both produce, both of them are excellent. I think Stanford Engineering School is excellent. MIT's is excellent. We have a lot of relationships backwards and forwards. Faculty sit on different committees. If you wanted to go by the ratings, so the rating systems, these people would rate MIT as the #1 engineering school. MIT works really hard to keep there, but Stanford works just as hard. So to me, the choice is they're both very, very good.
Thank you very much.
I think we can finish with a sentence: be an innovator, be an entrepreneur. Thank you.